Hi everyone, I'm Dingding Cai from Danbury University in Finland. Here I'm going to introduce our work on depth-based object 60-pose estimation. Many existing methods can accurately estimate the 60 pose for trained objects like PVNet, stable pose. However, these approaches only work for the seen objects and cannot generalize to unseen objects during the inference time. Latent fusion is proposed for performing 60 pose estimation for unseen objects. Similar to it, our approach, OVE6D, is also an unseen object pose estimator. Compared to latent fusion, our method is much faster and can be used for occluded objects. There are 3 stages in our framework. During the training time, our model parameters are optimized using the synthetic 3D object in ShapeNet. In the second stage, the trained viewpoint encoder in our framework is used for constructing the object viewpoint codebook. During the post-inference stage, our method performs the 60 object pose estimation from the given segmented depth image. For an object-centric depth image, the in-plane rotation along the camera optical axis does not affect the histogram statistics of the object depth values. Based on this observation, we proposed a viewpoint encoder for learning the object viewpoint representation, which is invariant to the object in-plane rotation. As can be seen from the picture, the same viewpoint usually results in similar representations in feature space, even though with different in-plane orientations, while different viewpoints usually result in dissimilar representations. To perform 60 pose estimation for unseen object, the object viewpoint codebook construction is performed for the target object. This is only performed once for each object in an offline manner. Once the construction is done, OVE6D takes the object instance segmentation and a depth image as input to estimate the 60 pose. In the first stage, we computed the object initial location and crop the object from the segmented depth image. Due to the object self-occlusion, this initial location estimate is usually inaccurate. In the second stage, we retrieve multiple viewpoint hypotheses from the codebook based on the cosine similarities between the depth image representation and the viewpoint representations. Next, we estimate the relative in-plane rotation between the input image and the retrieved viewpoint to obtain the complete 3D orientation. We can have multiple orientation hypotheses in previous steps. In order to find the best orientation proposals, we rank these hypotheses based on the consistency scores between the in-plane rotated viewpoints and the observation. As mentioned before, we can only obtain a coarse location estimate from the partially observed object point cloud due to self-occlusion. A refined step is thus preferred to obtain a more accurate location estimate. The details can be found in our paper. The evaluation on the line model dataset is shown in this table. Compared to latent fusion, our method is more accurate and much faster. Also, compared with other seen object pose estimators, our method still can achieve comparable result even without seeing any object in this dataset. On the T-less dataset, our method can obtain the comparable result without using ICP. After ICP refinement, our method achieves the state-of-the-art performance without using any image from this dataset. Here, some examples are shown to illustrate the process before and after the in-plane rotation. As can be seen in the first row, our approach can also handle the object occlusion. More examples on T-less datasets. To summarize, in this work, we propose an efficient, cascaded, and lightweight framework for performing 60 pose estimation for unseen objects without any additional parameter optimization. However, there are a few assumptions in our method. These assumptions may limit the application of OVE6D in some real-world cases. More details can be found in our paper. Thanks for your attention.